우리가 파악할 필요가 있다. 이거는 결국 뭐냐면은 이 사람이 한국인의 확률 근데 기분 H죠. 자, 요 확률은 리포트가 안 되는 확률이에요. 그렇죠? 누가 이런 거를 리포트하겠어. 근데 이거는 리포트는 안 되지만 우리가 요 반대쪽에 H 한국인일 때 H의 확률 혹은 한국인의 확률로부터 정보가 얻어낼 수 있다. 그러니까 특정 정보가 그러니까 우리가 갖고 있는 정보는 딱 갖고 있는 정보로부터 다른 뭔가 궁금한 것이 알고 싶을 때 우리가 베이지 시어럼을 쓸 수 있다라는 거를 그때 대해서 했었죠. 자, 그래서 자, 여기까지 질문 있으신가요? 이게 그러니까 기본적으로 컨디셔널 랜덤 베리어블의 개념이다. 네, 이게 컨디셔널 랜덤 베리어블의 개념이죠. 네. 질문 있으신가요? 네. 질문이 없으시면 네. 저기요. 여기 촬영하시는 분 마이크 갖다 주시겠어요? 네, 그러면은 네, 마이크를 달고 네. 다음에 익스펙테이션과 베리언스에 대해서 한번 배워보도록 하겠습니다. 네, 고맙습니다. 네. Okay, so let's think about a conditional random variable of x given y equal y. So this whole thing is a random variable. This whole thing is a random variable. One random variable, okay? Because of this reason, so it has expectations, definitely. So let's calculate also expectation of this one. So expectation is x given y equal to y. Okay? So this one is by its definition, it's x times f x given y x y and dx. So it is given in this way, definitely. So this is the definition. So here, this is the integration over x. Okay. So, but this y is the variance. This small y is like a random variable, but this y is a variable. That means this whole thing is a certain function of, let's use what's the maybe let's use f, certain function of y, small y. So conditional expectation is finally given as a certain function of small y. Okay, you got it? Okay, so the expectation is like that, so it's not that difficult to calculate it. But let's think about. But this y, but here, in this case, we are assuming that this random variable y is small y. However, this small y is also can be varied according to the PDF of y, right? So instead of using small y, if we express it just x given y as a random variable, this is a function of random variable y. That means this one itself is random variable, a random variable. Usually, expectation is not a random variable, right? Expectation is a fixed value. However, in the conditional case, this is the function of certain value. So expectation is also the function of certain value. If that certain value is random variable, expectation itself a is a random variable derived from y. So this is the derived random variable from y. Okay. Oh, yeah.
Second line, when you're assuming f as a function of y, are you just assuming any random anything like f of c or y like that, or just
Yeah, right. So in this case, there's any randomness, right? So in this case, this is not random. It's not the random variable at all. However, so in here, it's like that. In here, let's say this y can be y1, and this is the function of y1. But it can be also f y2, if y is y2. So that probability is actually given as, so the fy of y1. So because this y1, y2, y3 is that can be changed according to the the distribution of a large y. So if we just replace, or if we do not use this small y, if we just use the large y, random variable, then now this is a random variable. So this is random variable. Okay. Similarly, expectation of certain function of x and y given y equal y is also given as gx comma y and x given y or x given y dx. So this is also the integration of x. So it is also function of certain function of y. That means if we just use expectation of gxy given y, this is also a random variable. Derive the random variable from y. Okay? So let's calculate the variance. Variance of x given y equal y. So everything is the same. Everything is the same. So this one is, by definition, x minus, okay, this is by definition, this is the expectation of x minus expectation of x given y or y square. Okay, this is the definition. Then, given, there's already given y equal y. Okay, because the y should be held as a small y, as always. Okay, then it is equal to the expectation of the x square given y minus expectation of x given y square. Okay. So also, if we just use the variance of xy without specifying small y, then this is also the random variable. Derive the random variable from y.
it's not specified as always, right?
Yeah, right. So if we specify it as a small y, that means large y is fixed as a small y. Okay. Okay, so let's do go further. Okay, here we say expectation of x given y is a random variable, right? Then here, because if this is a random variable, so we can take expectation of this one. That means expectation of this one, right? I make sense. Then in this case, this one itself is totally non-random. Yeah, definitely. So let's calculate this one. So this one. Expectation of this one. So this one is integration. So this one is the derived random variable from y. So let's record. So let's think about expectation of how we calculate the GY. This one is calculated by G of small y and Fy of y, dy. So this is we all have already seen. So in this case, this G of y is this one. So okay, let's make it. So let's plug in expectation of x given y. So this is the gy here. Then here we need to put the Fy. dy. Okay. Then this expectation. This expectation is this one. Okay. So and here let's mark it. This is the integration over y. So this is the integration over y. And what is this one? This one is calculated by integration over x of x times f x given y dx, right? Times fy of y dy. Okay, so here this one is become, this one is integration over y, integration over x, and here is x is here, and this one and this one. So if we multiply x given y as a y, thus fy marginal, then the result is joint CDM, joint PDM, right? So if we multiply this one and this one, we got joint PDM. Okay, so this is fxy of x comma y dx and dy. So if we do the integration over y first, then this is the integration over x times integration over y fxy of x comma y dy and dx. So what's this one? If we integrate this joint PDF over y, whole range of y, then what do you get? Marginal of x. So this is x times fx of x dx. And this is the expectation of x. So this is the very intuitive result, right? Because this one is the expectation over y, then y is given at a certain value. Then if we integrate over y again, then finally we have to get expectation of x. So people usually note this kind of relationship using the subscript expectation, because the first expectation is for x, so expectation over x, and second expectation is for y. So sometimes we denote in this way. So first integration is for x, assuming that y is a fixed one, and second one is the iteration of expectation over y. Okay. So bottom line is this is the dx expectation of x. Similarly, it's not that difficult to get the expectation of y of expectation of f for x of gx given y is given as expectation of gx. Okay. Then this is very intuitive. This is very intuitive. Then let's think about this case. Then let's think about variance. Variance of x given y. This is the variance of basically the variance of x. And as I said, variance of x given y is another random variable derived from y. Right? Then if we take the expectation over y of this variance, what one of the value? Would it be equal to variance of x? That's a question. Intuitively, it makes sense, right? Because this variance is variance of the x when y is fixed to certain value. Then if we take the expectation over whole y, that seems to be the variance of x. However, you can see from the lecture, it's not true. This is not true. This is not true. Because the problem is because this is the kind of a variance of x, but in this case, this calculation does not include actually variance of y. So it's like that. So the x is actually varies, right? However, in this one is only the portion of the variance of x when y is fixed, and then y is also varied. So the variance of y should be included total variance of x. So actually, this the total variance of x actually is given as variance of, so the expectation of y of the variance of x given y plus variance of y of expectation of x given y. So actually the variance of x is given as expectation of variance, conditional variance, plus variance of y for this expectation of the conditional variance, conditional expectations. So this relation is called law of total variance. Law of total variance. But this kind of the relation is not that easy to prove by yourself. So then, if it's difficult, then just type of Google. So Google is the bar. So every answer is on there. Okay, so the bottom line is like that. Bottom line is these two is not equal. These two is not equal. That's the bottom line. Okay, next. Okay, so in order to check whether you understand it correctly or not, so please try these examples. And as I said, please make separate. Please prepare your separate note or your paper and write your the solving procedure on the paper. Then you need to submit that paper by the end of this class. At the end of this class. Okay, so please solve this problem on the separate paper, then submit it at the end of the paper, at the end of the class by noting your name and student ID. 자, 여러분 늦게 오신 분들 위해서 다시 설명을 드리면은 제가 긴 이야기를 짧게 하자면은 네, 어저께 CTL에 가서 네, 말씀을 듣고 왔는데 어떻게 하면 학생들을 좀 더 잘 가르칠 수 있는가 그랬더니 네, 이걸 시키래요. 네, 저를 원망하지 마시고 네, 저기 중앙광장 지하에 있는 네, CTL을 원망하세요. 네, 그래서 이거를 한번 해보라고 합니다. 그래서 실험적으로 한번 해볼 테니까 네, 이 문제를 푸셔서 네, 수업 시간 끝날 때 제출하시기 바랍니다. 물론 이거는 그레이딩을 하지는 않아요. 네, 단지 여러분이 얼마나 수업 시간에 이해를 잘 하셨는지를 체크하기 위해서 걷는 거고, 그리고 뭐 출석 체크, 그 다음에 뭐 참여 체크, 참여 정도도 체크하기 위한 거니까 네, 답이 맞는지 틀리는지 체크하지 않습니다. 일단 최선을 다해서 푸시면 돼요. Okay, so in this problem, so first, so you know the setting. So this is the joint x and y is this is the joint PDF of x. And joint PDF is only defined in this triangle, and it is uniformly, distributed over this triangle as a 2. And in this situation, please find the conditional PDF of y given x, and also find the conditional PDF of x given y. Once you obtain this, the conditional PDF, then please try to calculate, the conditional expectation and conditional variance. And please check whether, the expectation of the conditional expectation is equal to expectation of x, and also check the expectation of the conditional variance is equal to the variance. And at the end of your paper, please give some feedback whether this kind of the workload would be helpful or useful to you guys or not, or any of the any things you want to say, such a the workload. 자, 여러분 일단 쓰시고요. 네, 일단 풀어보시고 그 다음에 빈 공간에 아무데나 이러한 방식에 대해서 어떻게 생각하시는지를 네, 그냥 마음껏 의견을 게재해 주세요. 네. 물론 실명이라서 네, 마음껏 못하겠지만 그래도 네. 자, 일단 제가 한번 해볼 테니까요. Okay, so let me check your answers with me. 자, 이렇게 하면은 근데 그냥 받아 적으면 되는 거 아닌가? 애매하네. 예, 그것까지 안 물어봤네. 그렇네요. 그래도 해보는데 의미가 있으니까, 네. 아니면 지금 거둘까요? 네. 지금 거둬도 되겠다. 지금 이름 써서, 네. Please write your name. 괜찮아. 그러니까 다 푸는 게 중요한 게 아니라, 푸는 방법을 보면은 대충 어떻게 하는지 알 수 있기 때문에, 네. 그러니까 지금 10분간 시간을 줬는데, 이 10분간 시간 동안 자기가 얼마나 아는 거를 써냈느냐가 중요한 거기 때문에, 네. 네, 이름 쓰고 해서, please submit your paper. to the front. 자, 이름 쓰세요. 그리고 혹시 적고 싶은 말 있으면 적어서, 네. 자, 저기 뒤에서부터 앞으로 걷어주세요. 자, 뒤에서부터 앞으로. 자. 쭉 걷어서 앞으로. 네. 자, 뒤에서부터 걷었나? 네. 네, 쭉 걷어서 주세요. 자, 저기 뒤에서 앞으로 주세요. Okay, please submit. So I own, the check whether you are solving it, the right way or not. So I just check, how much you understand it. Okay? So you don't have to write, the correct answer. Just, your process of your effort is important. 자, 주세요. Lay. It's okay. It's okay. Like, can I have your sheet? Thank you. 예, 저랑 같이 한번 보도록 해요. Okay, so let's start from this. So basically, first, we want to calculate conditional random variable f y given x and f x given y. So it is f xy divided by f x, right? So this one is given, and we want to calculate this marginal one first. So let's calculate the marginal one first. F x of x is, in general, this marginal is calculated from the joint PDF by integrating over y from -infinity to infinity in general. However, in this problem, this y's range is from 0 to x, and within this range, the joint PDF has a constant density too. So here, the integration range is from 0 to x, and this function is 2 dy, and this is a 2x. This is a 2x, and in this case, x's range is from 0 to 1. If it's outside of this range, the PDF is 0. So formally this one is 2x for this one, or 0 otherwise. Okay, it's the right one. Then here, our goal is the f y given x. Y given x is given as xy is 2 over 2x. This is 1 over x. But importantly, 1 over x, what's the range of the 1 over x? Because y is limited from 0 to x. So this is, if y is from 0 to x, it is given as 1 over x. Otherwise, 0. Okay? So similarly, you can calculate f x given y, which is, if you calculate it, write it in a right way, so it is 1 over 1 minus y when x is between y and 1 and 0 otherwise. 네. 이거요? 이거요? 아, 예. 아니에요. 괜찮아요. 예. 뭐. Okay. Okay, here. Let's think about. So what is the, the distribution of these conditional ones? What's the distribution of this conditional random variable? One of it, we already learned. So as the usual random variable, we have learned there's the uniform and the normal and exponentials. So one of which one this conditional random variable has? Okay, again, so this conditional random variable is for y. X is a kind of parameter, right? So this random variable is for y. So regardless of y, this random variable has a value of density of 1 over x. It is constant regardless of y. So this is uniform. Uniform over y. 이해가 되시나요? 이 아이의 유니폼이라는 게? Okay. This one is a uniform distribution over y. Because whatever value of y, the density is 1 over x. For all of y values, that is uniform. Right? This one is also uniform. Okay? 그쵸? 유니폼하죠? 왜냐면 x 값에 상관없이 density가 다 똑같은 값으로 주어져 있잖아요. 그쵸? 일단 이건 y가 픽스되어 있다고 보는 거죠. 그쵸? So it's uniform. Okay, so then let's calculate expectations. Okay, expectation of x given y equal to y is given as, because it's up for x, so okay, here I'll calculate this one. So x is defined from y to 1, non-zero to y to 1, and we times x and 1 over y1 dx. Okay, this is x, and this is a PDF of conditional random variable. And the range is from y to 1. So if you calculate it, and you have 1 plus y over 2. Similarly, variance of x given y is the same. y1 x squared times 1 over 1 minus x dx minus 1 plus y over 2 square. 그쵸? If you do this one, this calculation, it is 1 minus y squared over 12. Okay, so let's calculate expectation of this expectation. That means expectation of x given y. So here, this one is calculated. This one is, we already get this expectation is given as this one, and the outer expectation is expectation over y. So here we use 1 plus y over 2, and we have to use the fy of y. This fy, so marginal of the y is given as 이게 저걸로 주어지죠. This one is given by 2 times 1 minus y dy, and the range is, and its range is from 0 to 1. Okay? So if you calculate this one, then you see 2/3. Okay, then we already proved that this one should be equal to expectation of x itself, right? Expectation of the x itself. So let's calculate it. Expectation of x. This one is from 0 to 1 to x times what's the marginal of x? Marginal of x is calculated of 2x, right? This is the marginal fx of x, marginal PDF of x, dx. Then it would be 2/3. So it's the same. Definitely, it should be. Okay, so we have checked this one. Then let's calculate the expectation of the variance. So expectation of over y of the variance of x given y. Okay. Okay, this one is calculated by integration over y, and for this one, 1 minus y squared over 12 times. Then what's the PDF of y? Marginal PDF of y is given as 2 times 1 minus y and dy. And here y is from 0 to 1. So if you calculate it, it is given as 1/12. 24. Okay. So if you calculate the expectation of this variance, so this variance is a certain function of y. So that function is this one, and this is a PDF of y, marginal PDF of y, and this is a certain function of y, right? So it is given in this way. However, if you calculate the just variance of x, just variance of x is given by expectation of x squared minus square of the whole expectation. So this one is x squared times marginal of x is 2x dx from 0 to 1 minus this one is already calculated as 2/3. So square of the 2/3 is 1/18. So definitely this one and this one is different. This one is larger. Always should be larger. Okay. So we actually shows that these two is different, but expectation should be the same. Alright. So 자 여기까지 하시고요. Any question? 질문 있으신가요? 네, 질문 없으시면 여기까지 하고 다음 시간에는 인디펜던트에 대해서 공부해 보도록 하겠습니다. 네, 수고 많으셨습니다.